All right. Hello, everyone. Good. So let's continue the discussion we interrupted yesterday. So yesterday, we studied the microcanonical, the canonical, and the grand canonical ensemble. And we have seen that we're characterizing the ensemble properties of fluids. We're interested in quantum fluids at the moment. By, for example, looking for the free energy, the grand canonical energy in our case, because grand canonical because we are interested in systems that are not closed, where the number of particles is going to change according to the chemical potential that we have encountered. Chemical potential that is going to define and rule the equations that concerns reactions, okay? For creation and destruction of particles, because they are going to change, to transform one in another through the reactions that they have during their encounters. Encounters that are pairwise, so there are always two-body interactions, where we can have a reaction that is proceeding in this direction, creating other two particles, that's in general. Could be also the same kind of particles, if we're talking about scattering, for example. Or we can have a reaction such as a positron, electron giving two photons, and so on and so forth. I gave you a few examples. This would be a reaction proceeding in this direction. We might have the reaction proceeding in the other direction as well. And actually, this occurs simultaneously, and we have, at the equilibrium, we have an equality. So we have a transformation of particles in this direction and in the other direction that compensate one each other. Therefore, we have this equilibrium that is going to take place. Using our phi, then we understood that we can derive very easily, just by looking at derivatives of this function with respect to the volume, the temperature, and the chemical potential. We can derive the entropy of the system, the pressure, and the number of particles. All right? Therefore, with this guy, we can have a good characterization of our quantum fluid. Moreover, we continue our investigation in which we consider the bosons and the fermions. And we made a distinction between the two because those kind of particles can obey or not, fermions or boson, the Pauli's exclusion principle. And this defines how the occupation is going to occur given a certain state. So if we have an alpha state, see our box in our 6-dimensional phase space, we can have one particle or no particles. If we are talking about fermions, that's because we can have only one particle in a certain state, wherever for bosons we can have as many of those. And this creates the distinction that leads us to the derivation of their distribution that is different. So we are going to have the occupation number, so that the probability of having a particle in a certain cell of the space for bosons, and one for fermions, and the two differ. They're very similar functional shape. There is a plus and minus that makes them differ, but they are very different in nature. As you see, that's because of the inner properties of the particles. Now we shall continue. We know how the particles are going to populate the phase space diagram in equilibrium, for example, and if they are bosons or fermions. Now what we can do is to characterize and start to play with an actual fluid. Therefore, we are going to characterize a quantum gas, a gas composed by quantum particles. And what we are going to consider is an ideal quantum gas. So, what are we going to have? As I said, a gas, therefore the number of particles is extremely large, right? And in all the distributions you have seen, we have all symmetries. But in this case, if we go for a very large number of particles, we can approximate symmetries to integrals. right? We go in the limit of an infinite large number of particles in a certain volume. So we go to the continuous limit. Meaning symmetry becomes integrals. Then we can characterize the particles. Because all those distributions were referring to the epsilon, the energy that a certain particle can have, and to the momentum. Therefore, we know that our momentum is h bar k, as we've seen at the very beginning of the lecture. So you see that what we studied then is coming handy also now. And the energy of a particle, given its momentum, is going to be given by the momentum of the particle squared plus the rest energy. So we have two contributions. One is referring to the rest mass, and the other to the kinetic energy, which is captured by the momentum. So to be specific, to be more generic, don't say kinetic energy, but say momentum, because these also include massless particles, where m is equal to 0, but they still have an energy content that is going to enter in our equations. Then we are going to consider confined box. That allows us to have discrete k modes, okay? Discrete momentums. That's because, as we said, the phase space distribution is discretized in the cells that are given by the uncertainty principle. Okay. Therefore, to create this discretization, what we just have to do is to consider, a certain length. Let's call it L. And then we can have modes that are oscillating in this way. So they are discrete because they have to end up at the zeros at the extremes. So we have this mode. So we have one wavelength, half a wavelength, and then maybe this is not exact as a drawing. Then we have a third, a fourth, and so on and so forth. Okay, such that this condition is respected. If we do that, our K mode is going to be 2 pi over length. That's the wavelength, right? Normalize over is the inverse of the wavelength, normalize over 2K. That's just for the definition of K. That's how it is defined. Times N, where N is 1, 2, 3, 4. 1 wavelength, 2 wavelengths, half, and so on and so forth. Okay? With that, we have a number. To this number of modes, we can define a volume, which is just, the length is the volume to the power of 1/3. That's it. So what I did, I just isolate this term, and then I relate the length to the volume, this volume of the box, of the scale that we are considering. Therefore, this is what I want to go. In the end, is to derive a dn, such that I can have an integral and quantities that are discretized with respect to the mode in relationship to the steps, right, in K. That's what I want to do. And what we have is a three-dimensional object. That's why I introduced the volume, a three-dimensional space, sorry. And therefore, I just make all of it to the power of 3. And then, you see, you just compute. Give me another color. dn dk. That's it. Then, what we do, we include the internal degrees of freedom, G. For example, the spin. Okay, particle can have different spins, and for the different particles, for example, we need to include different G's. Therefore, the n is going to be g volume 2 power of 3 the cube x. I just included the g. Then what we want to do is to link the momentum to k modes, so that the integrals are going down with respect to k modes. And that's going to be handy afterward. So we have that. So, sorry, I'm going to relate the k modes, what's this x, that's a k, to momentum, so that we have a direct relationship with the momentum of the particles. And I just use the definition that, the quantity that it relates, we are just using the definition of the k mode with respect to the momentum, and there is just the h bar k. That's coming from here. So we have our decay, and we plug it into here. What we have in the end is gv over 2 pi h bar, all to the power of 3, dp to the power of 3. Okay, so here we have the number of states in intervals of momentum. Then what we do? We want to compute, for example, the number of particles that we expect. So we know, we have already seen that it is nothing but the total number of particles, just the sum of, with respect to with respect to the number of particles that we have in all alpha states, in all boxes. And the Bose-Einstein and the Fermi-Dirac distributions that we studied yesterday just tell us what is an alpha is for the macrocanonical, for the grand canonical ensemble in equilibrium. Well, actually, also here we consider the mu, so it can also be not minus n plus 1. So Fermi-Dirac and Bose-Einstein distributions. Then, having that, what we said, we have a symmetry, we have a very, very, very large number of modes, and we go in this limit. Symmetry are going to become integrals. For our n is going to be the integral of n alpha with respect to the n, where the n is the difference in number. We have a relationship between the n and the k, the p, which is given by that. Therefore, we can transform this integral that is over the n in an integral over the p. Yeah?
The big N is like in the volume box, so it's equal to the small n to the power of 3. We have the n for the small n to the power of 3 equals like we have the cube.
Up here. Yeah.
Yeah, for the small n, and now we have the big N.
They're all n. They're all big n. I don't see small n's.
No, like we started with the small n.
Ah, here, sorry. It's the same n.
So, but
Yeah.
But it's not to the power of 3, the big the n to the right? It's not to the power of 3, the n? Yes, on the left side on that equation, we have the n.
Yes?
Yes, but not to the power of 3, whereas the rest are like some lower volume.
No, that's nonsense. Okay? I mean, sorry. The n to the power of 3 is the number in the volume.
In the box, yeah. So
Yes.
that's defined as,
So we go from the volume to the box.
yeah. And then the
Okay?
big n is like.
And that's that one. Exactly. And that's in the box.
Yes.
Okay, perfect.
Between the small and
Yes, yes.
Okay, thank you.
Okay. Here, we go from the length, we go to the box. Okay. And that's the m cube. All right, where was I? Yes. So what we're going to do is now to transform this integral in an integral with respect to the momentum p. All right, where the n is going to be given this relationship, so the n is now over the p cube. And, well, sorry, that's confusing. So the n is going to come from here, and alpha is nothing but that. But yes, is a function of the alpha state, but epsilon alpha is a function of p. Okay, contains the energy and therefore p. Therefore, this one is a function of p. And what we get is an integral between minus infinite and infinite, because we are accounting for all possible momentum. E epsilon minus mu over kt plus minus 1 in gv over 2 pi h bar to the power of 3 the cube. Now we are talking about a fluid which is in equilibrium. We do not expect to have gradients. In any case, we are assuming a universe which is homogeneous and isotropic. Therefore, we don't have any gradients. Therefore, all directions of the p modes are equivalent. All right? And it's therefore convenient to move to polar coordinates. Well, basically, the three-dimensional interval in step in the momentum is equal to 4 pi, so that's the entire solid angle, times p squared, the p. And then, if we want to go to densities, we just have to divide over 1m to get densities. So we just work out this very same integral. We divide by the volume. And therefore, this volume, which is quite arbitrary, disappears because we are just dealing with a density. What we are left with is n equal to g over 2 pi h bar to the power of 3 integral between 0 and infinite, because we are integrating with respect to the modulus of p now, because it's just the radial, right? It's a polar coordinate. 4 pi p to the power of 3 dp over e epsilon minus mu over kt plus minus 1. That's the number density of the species that we are considering. Do we want to get the energy that the system is storing? What do we do? We just get the very same expression over 2 pi h bar to the power of 3, integral between 0 and infinite, of 4 phi p to the power of 3 dp over e to the epsilon minus mu over kt plus minus 1. And what we do, we just add the contribution of each individual p, the particle in p. Therefore, we just add epsilon p. That's the only difference, right? Here we are counting. For each count, we add a contribution of epsilon p. Yeah?
Why do we have p to the power of 3 in the integral?
Sorry, mistake. It's polar coordinates, so this must be a 2. Thanks. All right. And we have the energy density, therefore. So you see, it's clear that to the energy density, you have a collection of particles, and all of those particles contribute with a different energy. Energy that depends on the p, the momentum. And p and the energy, remember, is coming from here. All right? Now what we can do? We can define the free energy. And the free energy phi, we have seen that is equal to kt, the logarithm of the grand canonical partition sum. And if we want to have it explicit, we just have to plug in the explicit form of the grand canonical partition sum. Since we have many different energy levels, each of them is going to contribute. Remember that there was this productory. We had the partition sum, which was a summatory. In the exponential, there were the sum of two quantities. The exponential of the sum of two quantities is the product of two exponentials, and with that we split it. Therefore, we have now the product for the z alpha, where this is the distribution for each individual alpha state. Now we continue. Minus kt, I'm not going to touch it. And this is the logarithm of a product. I'm just now going to exploit the properties of the logarithm. And the logarithm of a product is the sum of the logarithms. Just that. For we have the sum over alpha, logarithm of z alpha. Okay? So just the properties of the logarithm from this step to this step. Nothing more than that. Logarithm of a product, summatory of a logarithm. All right. And now here we specify our Bose-Einstein distribution or the Fermi-Dirac distribution, which I wrote. Got the glasses. Where was it? Here, which I wrote here. So the partition sum, sorry, for the Bose-Einstein distribution. And we've seen in the previous lecture that they are 1 plus e to the minus epsilon alpha minus mu over kt for the Fermi-Dirac, and z alpha, so Fermi-Dirac, and this is for the Bose-Einstein, is 1 minus e to the minus epsilon alpha minus mu over kt, and all of it to the power of minus 1. That's the Bose-Einstein distribution. And now what do we do? Look what we have here. Here we have a summatory, right? Continuous limit, the summatory is going to become an integral. Let me write it here so that we have it together. Therefore, our phi for a fixed temperature, volume, and chemical potential is going to be equal to minus and plus, and the minus and plus depends on the Bose-Einstein or the Fermi-Dirac distribution, GV over 2 pi h bar to the power of 3. These are just constant, therefore I can bring them outside of the integral. The summatory that turns into an integral, again, we are going to do that in the polar coordinates, 4 pi p to the power of 2 logarithm, I don't fit here, where do we put it? In the p, where this guy is equal to 1 plus minus the exponential of minus epsilon, function of p, minus mu divided kt. All right. So I continued along this line. Phi definition. I used the definition. I split the contribution of the grand canonical ensemble with the contribution of each individual alpha mode, which is coming with this product. I used the logarithm properties of the properties of the logarithm to have a symmetry of logarithm instead of a logarithm of a product. And then I plugged in the distributions that we have for the Bose-Einstein and the Fermi-Dirac into this definition. So I'm just continuing here. The symmetry becomes an integral. And exactly as we did before, I made the integral in polar coordinates, because again, we are talking about something isotropic. No direction is different from another. And these minus and plus are just for the Fermi-Dirac, for the minus, and the Bose-Einstein that requires a plus. Okay? And this wiggly thing here is all of that.
Isn't there a KT missing as a prefactor from the potential on the bottom line? Or we have the KT times...
Oh, yeah, right. I forgot the KT. KT, they're fixed because the temperature is fixed. It comes out as how we do integral, and then we have GV. Yes, thanks. All right. Once we have that, it's fantastic. We have phi, and what are we going to do? Exactly what I said earlier. Once we have phi, we can compute all of these quantities. So it comes very handy. It's just a derivative, nothing complicated. For we're going to have the pressure that we have seen is minus. We are going to compute for the pressure. We are going to compute the entropy. And we are going to compute, if we want again, n to rederive it with respect to the phi as this derivative. All right? So these are just all the derivation that we can do. Now I'm not going to, do all of that again. You find it in the notes. That's exactly along the line of what we discussed yesterday. All right? That's thanks to phi. All right. Now I will just give you an example, because here we are talking about particles, Bose-Einstein distribution, Fermi-Dirac. It's still very generic, right? Let's take an example for photons. So that's easy, because the mass of the photon is equal to 0. Therefore, the energy is going to be Cp. That's easy. We are talking about equilibrium. Therefore, mu is equal to 0. And is a boson. It's a boson. Therefore, we're going to use Z alpha. Well, let's write it anyway. 1 minus E minus Cp over Kt, all of it to the power of minus 1. So we just use the expression up there. I don't do the steps, just to let you know that the integral between 0 of infinite in the p can be easily solved by a simple variable substitution, where we define x as Cp over Kt. Then the integral is very simple. So phi equal to that. We just make this integral substitution, this variable substitution, and we derive this expression, minus Gv p to the power of 2 over 90. Kt to the power of 4 with respect to h bar c to the power of 3. That's our free energy for a photon. I give you also the pressure, 3b, which is equal to minus the phi over the v, equal to g pi square over 90, Kt to the power of 4 h bar c to the power of 3. That's our pressure. And then we have the entropy, S for the boson, which is minus 1V, the phi over the T. And, well, let's write it since I did the effort in now. K 2 pi to the power of 2, 45, Kt over h bar c, all of it to the power of 3. Right? And we can do the same for all the other kinds of particles. So before showing you the other ones with the computer, I'm not going to do all the derivations because it's always the same. Let's just make a fast recap. So now we are dealing with quantum gases for an extremely large number of particles. And we can adopt the continuous limit, where all the symmetry that we have seen in the previous lecture yesterday, when we introduced the partition sum and so on, are going to become integrals. We are using the particle properties, so we can link the momentum of a particle to the K mode. Okay, the two are related by this h-bar relationship. We know that each particle is carrying an energy due to its momentum and a rest mass energy, if they have a mass. We are quantizing our system by placing it in a box, and we are counting modes that are like that, and they are discrete. Therefore, given a certain wavelength, given a certain length scale, K is just 2 pi over L, and this is just the definition of a single K. Then we can just multiply by n to have all the possible other discrete modes, where n can be 1, 2, 3, and so on. So you see, K goes the way around with respect to the momentum. So if K is large, the wavelength is small. Okay? Nice. Then what we did, we start to compute the spacing of our phase-space diagram. We just used this relationship just to get this. And the length is just 1 over to the power of 3. Three-dimensional case, and we have the n to the power of q. So all of this expression is just to the power of 3. We included the internal degrees of freedom, where g is equal to 2 for photons, right? Because these are the two polarization modes that they have. We linked back the p to the k, and we got this expression. So we have the n, so the integral on the n, this guy here, multiplied by g and expressed in terms of the momentum p. Then we went to, for the evaluation of the total number of particles that we have, where we have to plug in the distribution of the particles in the alpha modes given the specific kind of particles that we have, fermions or bosons, with the plus and minuses here. We just express the n's with respect to the integral, and with respect to the momentum, and that's what we get. We go to polar coordinates. That's important because we are assuming homogeneity and isotropy. Therefore, all directions are equivalent, no matter which angles we are going to take. And here we get, simply, we get the number density after we divide by the volume. You see it appears here. Here I just divide it, went to polar coordinates, and that's the expression. Nothing more than that. If we want the energy, internal energy of our system, these are counts of particles, and each particle carries a certain amount of energy. Therefore, if we want internal energy, we just integrate over all the energy distributed according to the number of particles that we have given their alpha modes, states. Then we can compute the free energy very easily because we just have this definition. I skip all this kind of step. We plug in our distribution for the Fermi-Dirac and the Bose-Einstein distribution, so for fermions and bosons. And that's it. Again, we just transform, as we did in analogy what we did earlier, this symmetry into an integral, and we get our final expression. If we now want the other properties of our fluid, we just use the derivatives of phi to compute, for example, the pressure and the entropy. And that's what we did explicitly for the photons here. So here we have got an example where I set the mass of the particle equal to 0, because that's photons are massless. That's the energy of the particle. This is nothing but this expression with m equal to 0. That's this one. We are considering equilibrium, therefore mu is equal to 0. The chemical potential in equilibrium is 0. We are using the boson, the boson, we're using the distribution for the bosons, which is this one. And we just plug it into there with this simple assumption here, and that's the expressions that we get. We get the chemical potential, out of which we can get the pressure, out of which we can get the entropy. All right? For the other particles, is exactly the same. There's no difference whatsoever. Just show you the relationships so that you have at least, that you anyway find also in the lecture notes. And here they are. So for all other particles, with and without approximations, that's what you have. So you have relativistic particles, these guys, for bosons and for fermions, right? Then here you have the number density, you have the energy density, we have the pressure, and you have the entropy. Explicitly, here, I computed this guy here, right? So look that there is this expression going from here to here. What do you see? You have the degrees of freedom of fermions divided bosons. Okay, this is just a way of writing this expression in a compact form, because we have NB, which gives you the functional form. You divide by GB, so you get rid of this one, and you multiply by GF. Okay? So this guy here is nothing but all of that, where G is for fermions, and the only difference, therefore, is this factor of 3/4. And similarly for the others. What else can we do? This is for particles with that are relativistic. Look, I'm considering a relativistic energy. But if we want, we can also go to the non-relativistic limit. And that's easy. That's easy because with all what we have, we just need to apply the approximations that are relevant. The user doesn't work. There's another one here. Okay, right, better. Okay, so what we have to do is to substitute the energy of the particle from relativistic to non-relativistic. So we just apply a first-order approximation. And the partition sum is going to be this one. That's from the Boltzmann distribution. And the rest follows. It's just the usual integral. You just go through and you derive these quantities. So look what happens here. Here we have a dependency with respect to the temperature of T to the power of 3. I have to stress this because that's a very relevant difference between relativistic, so T to the power of 3 for bosons and fermions. The dependency is T to the power of 3. For the in the non-relativistic limit, we have T to the power of 3/2, not 3, 3/2 plus an exponential. That's the exponential cutoff of the Maxwell-Boltzmann distribution. So this cutoff is telling you that for non-relativistic particles, you have you basically have a number of particles for large temperature, which is very, very, very small. Okay, there is an exponential cutoff. You don't have these high energy tails. You don't have these you don't have many particles with large temperatures. All right. Good. Nice. So at this point, I think it's a good moment to stop. we can have our little break. I already did the summatry of all that, so I don't need to do it now. And later we will continue with the reaction. So now we know how to deal with quantum gases because we know what is their pressure. We know what is their density. We know what is their entropy. We have a characterization of the gases. Having that in store in our repertoire, we will continue with the reactions where I'm going to give you more details. So I'm going to give you a collection of equations that allows you to follow the evolution of the reactions as a function of time, or if you wish, as a function of temperature. Temperature depends on time, reaction depends on temperature, and they're all related, okay? So that's what we are going to do in the next lecture. We can resume at 15 past. Well, let's try to finish earlier. So let's do it in 10 minutes, that's sufficient. So at 10 past, we will resume the lecture.